Welcome to today's Andony lecture featuring our speaker Andrea Brovelli from the Institute for Neuroscience at La Timone at CNRS and Aix-Marseille University in France. Hello, Andrea. Welcome. I'm really happy to see you at Andony.
Hello, hi, Michael. Thank you very much for the invitation. I'm really looking forward for this seminar.
Sure. Our brain, I guess, is without a doubt one of the most complex dynamical systems that we are currently investigating with large-scale efforts in natural sciences. And probing this dynamic activity displays nowadays a large number of parallel time series that allow researchers to gain insights into this black box called the brain. One approach to do this is to study the correlative and causal interactions displayed by these time series. And today, Andrea will give us an overview of some of these methods that fall under the general heading of functional connectivity. He will also present to us a practical tool on how we can apply these approaches to our own data. So, Andrea, I guess there's been a lot of progress in the development of these approaches over the last, say, 10, 20 years or so, no?
Yeah, absolutely. Actually, it's probably even more. Actually, I started my PhD in the last century, so in 98. And so it's already like 25 years probably that people have been trying to study brain interactions and how they make sense for cognition. So yes, the topic and things have evolved. Some methods have disappeared, some have been consolidated, I think. So I will try to give an overview of the theory and then also the methods in 2024-25. So the framing of my talk, at least the theoretical part, reposes on some questions about how brain areas interact and how they support cognitive functions. So I will go through some basic questions and some important literature papers. So let's go. So the working hypothesis behind our work is long-standing hypothesis, suggesting that cognitive functions and neural computations, they emerge not from the activity of single neurons or single brain areas, but from the coordination and through the interactions of distributed neural populations at different levels, being single neurons or brain areas and circuits. So if you want to have a look at some basic, some pretty old but still relevant reviews, you can have a look at the so-called brain web hypothesis that was put together, was developed during the 90s and then framed by Francisco Varela in this Nature Review in Neuroscience, in which function integration is thought to be to emerge from the coordination of functional specialized circuits. And also, I mean, going back even to from Hebb cell assembly hypothesis, suggesting that sensory input or the sensory processing or the production of behavior outputs emerges from the coordination of spiking activity at the level of single neuron populations. So the question is, how do we study by looking at the brain activity, by measuring the brain activity of single neurons or single brain areas? How can we characterize and how can we measure, how can we quantify these processes? Still in a theoretical point of view, you can frame these processes also in the so-called dynamic system theory, in which you have a link between a structural connectivity between neurons, between brain areas, which is normally thought to represent like the highways where the information flows, so the roads where information flows, and then some dynamic repertoires that could be, say, the traffic over these roads, then they collectively produce some states here, which some hypothetical and abstract representation associated, say, to given perceptions or given behavioral output, that then they produce some markers, some effects, something that we can measure by looking at the brain activity, and some kind of functional connectivity measure or some functional connectivity dynamics. So the dynamics of the functional connectivity, that is actually what we want to measure and characterize. So basically, the questions that we are, there are two main questions that we are trying to answer with our techniques. The first one is, what are the so-called interaction rules? So are there some kind of basic mechanism behind the interactions between brain neurons or brain areas? Can we learn these things by looking at the data only without any kind of model behind, in a kind of data-driven approach? And if these states that we can characterize, say, synchronization states in the network and so on, do they have some kind of functional meaning associated to cognitive processes? And I suggest you to have a look at this chapter. They came out in 2020 in the Cognitive Neuroscience. If you want to have like an overview of the main questions and the main methodology of these techniques. So yes, yet another example, more recent example of why do we want this? So there are some facts, some scientific facts that suggest that information about stimuli, for example, here, are encoded in the interactions between neurons. This is an example of a paper in which the information about the visual stimulus is encoded into interaction that can even occur at a higher order, such as triplets or quadruplets, or even between pairs of brain regions, between single neurons. They encode more information than the activity that is encoded locally. And if you want to have a recent review on the topic, you can have a look at this paper from the lab of Stefano Panzeri in Hamburg, now in Germany, which makes a nice overview of the state of the art behind the relation between structures and functions, and specifically related to what is encoded at the level of neuron population codes and the correlation between structure and function. Just to give you an example, there are different theories, such as like we may have like an independent population code in which like two stimuli, like orange and blue, that are encoded only at the level of the activity of single neurons. But then again, the experimental data is suggesting that something is happening also at the level of the interactions, at the level of the correlated population code, in which the correlations between neural populations, and so the pairwise correlations, they can be used to encode information about the type of stimulus. And also they make some nice links between the observed collective behavior that is observed in neurophysiological data and what could be the computations, or what could be the functional roles in the brain. And they make some suggestions, such as that these correlated population code may be helpful in addition to information encoding, also for the creation of different encoding at different timescales, but also it could be helpful for an effective broadcasting or the propagation of information in neural circuits at different levels. Okay, yet another example, which is a bit older, now talking about more large-scale neural interactions. This is a review paper from Marcus Siegel, in which he put forward the idea that these interactions, they do not actually emerge at the level of the firing rate of single neurons or the spike timing of single neurons, but also through what are called neuronal oscillations, such as mesoscopic or macroscopic collective dynamic behaviors, such as synchronization phenomena. And in this case, they suggest, and these are working hypotheses that different labs in the world are trying to test, is that different processes could be brain states, for example, such as the processing of visual information or auditory information, or say the production of a certain behavior. They are associated with different patterns of local activity. On the other hand, what they suggest is that the encoding of a given process is not only understandable only by the local activity, but is something that is emerged through the collective and coherence oscillations that are present through in the network. And see if, for example, and that this actually could emerge and could be linked to different computations that they subserve different cognitive processes that could be differentiated in terms of the frequency of the coherent oscillation, say from lower, say the theta and alpha, to the higher frequencies such as the green, such as the beta, for example, or the high gamma oscillations. And these are called the so-called spectral fingerprints that we are all looking for in the brain data. And so to make the link between the cognitive processes and the underlying computations, how in a kind of hardware by means of what they call the spectral fingerprints, which is a kind of generic definition, but is linked to the fact that the underlying processes are related to coherent oscillations at different frequency bands, and that these coherent oscillations and collective behaviors, they can be dependent on the frequency and also can be dynamic in time during a task. Okay, so I think I went through, like, these are some of the relevant, and it's not, so this list of reviews is not exhaustive, but I mean, I would suggest you, if you want to dive a bit deeper into the theoretical reasons why we try to understand large scale or mesoscale interactions, I would suggest you to have a look at these papers. So now let's go down a bit more into the practical side of the questions, which I think is something that you're more interested since you subscribe to this school, which is how do we, in practice, in a reasonable time given by the PhD duration of the PhD, which is a few years and not 10 or 15 years, how can we do this from our data? So basically, what we've been trying to put together in the last 5 years, probably this project started around 2018, 19, starting from methods that I had been working on in the past, was to try to have a single framework in which we could do both both an analysis of the local specificity of brain activity of single brain areas or single neurons, and then combine with the functional connectivity analysis in a task-related condition. Just to go a bit step even prior to these definitions, so functional connectivity is defined as a set of metrics which allow us to study statistical relations between time series, neuronal time series. So the idea is to try to infer from the activity of single neurons the traffic or how these two neurons or two brain areas they interact. This is not straightforward because, say, this is something that in network science sometimes is not done, because in network science you may have already direct access to the link between two brain regions, two nodes of the network. Say in social network, you know when you are sending an email, so you have a direct relation between two nodes. In neuroscience, most of the time, we are trying to infer the relation between the nodes of our network from the activity of the single nodes. It's like trying to infer the traffic between Paris and Jülich, for example, by looking at the traffic present in Paris and in Jülich, and you try to infer what is the traffic over time between the two cities. So this is, as you may understand, is not an easy task. So there are lots of things which are hidden, so lots of assumptions that you have to make. And basically what we want to do, what we try to do in functional connectivity analysis is exactly to develop the best methods that allow you to calculate, infer the statistical relations between the nodes of a network in a specific way, meaning that we want to know whether the statistical relations are related to a cognitive process that we are trying to understand. That's why you see here the term task-related, meaning not in a resting state condition, but mainly functional connectivity measures or metrics that are associated to a given task. What we, and I will show you later, what we ended up using is a set of measures that come from information theory, IT here. And you will see later that information theory provides some measures and some tools that can be general enough to be applied at different levels. So that's why we are focusing on these measures. And the second block of methods that we wanted to combine was a set of statistical inference methods that are normally applied on neurophysiological data to see whether the activity of a single neuron or a single brain area is statistically relevant for a given task. Our goal was to have the same type of group-level statistical inference methods, both for the analysis of local activity and function connectivity analysis. That's why you see this. This is the paper describing the methods for this type of tools. So our toolbox is based on some measures from information theory, and the underlying formalism, the underlying maths is actually pretty simple, and a few methods are already dating back from Shannon's time. So from classic information theory, in a one-page information theory for dummies. This is a bit too fast, but I will try to go through the basic measures from information theory, which has been developed in to quantify and define what information is from data, how it can be stored, and how it can be communicated in a network. So the basic measures are surprisal, the entropy, image information, and so on. So now we'll go through them very from the basic point of view, very rapidly. So I hope it will be clear enough. But if not, if you need to have a look more at the basics, I suggest you to go and look at the Wikipedia page on information theory, which should be kind of enough to give you the mathematical background for the methods that I will show later. So the Claude Shannon, so the geniality of Claude Shannon has been to formalize from first principle what information meant to him, and to formalize this in a way that can be calculated from data, and especially linking probability theory with what emerged to be as information theory. The very first measure is what is called the surprisal. So the surprisal is very simple. So if you have a look at this function here, so the logarithm of function is something that is minus infinity if you go to 0, then it's 0 if it's 1, and then it goes up in a logarithmic fashion. The negative of the log function is exactly this function here, which is infinity. It goes to infinity as we approach to 0, and then it's 0 if we go to 1. On the x-axis, you have the probability of a certain event, and the surprisal is defined as the negative log of the probability value. Why is it called surprises? Because it's kind of related to the psychological idea of surprisal of an event. Imagine you don't know what is going to be the price of a coffee that you go in the bar every morning. So you're going to a new country, and so you may say, okay, it could be like €1, €2, or even €5. You're kind of uncertain about the cost of a coffee. So you may have say the probability of a coffee costing like €2 is going to be something like 20%, 0.2. So once you order a coffee and once you have to go and pay your coffee, you will be kind of surprised by hearing that it was only only €2. On the other hand, if you go in a bar in which you've been going every day, you know that the cost of a coffee you're sure about it, is €1.50. Okay, so the probability of paying a coffee €1.50 is 1. Okay, so once you go to pay your coffee, your surprisal will be 0, because you're completely sure about the outcome, which is the cost of the coffee that you're actually paying. the lower the probability. So for a very like remote or very remote event, such as I don't know, like winning like a lottery, the surprise will be extremely high. So this definition of surprise is extremely linked to the measure, to the definition of entropy, which is nothing but the average of the surprisal over a certain number of events, n events. So here the sum of the probability of the negative log. So this is definition of the average of the surprisal, give you the average amount of uncertainty in a given variable x. Again, going back to here, for example, if instead of having the cost of a coffee, but having this is the uncertainty in a coin tossing, in which you can always only have two outcomes, either head or tail. Okay, if you have a coin which is completely unbiased, so that it has 50% of falling on head and 50% of falling on tail, the uncertainty is at the maximum, because you don't know what is going to be the outcome of the next toss. On the other hand, imagine that you have a coin which is biased, which falls on 99% on head, okay? So the probability of head is going to be 99%. The uncertainty will be very low, because you will be able to predict what is going to be the outcome of the next toss. This definition of entropy, which is related to the average amount of uncertainty in the next toss of the coin, for example, can be defined, and this was the geniality of the genius of Shannon, defined also as the amount of information that is carried by the next value of x. Meaning that if you're in a condition in which you're completely sure what is the sequence of outcome, imagine that in the coffee example, on the bar example, you exactly know that the coffee in your bar next door costs €1.50. The fact of knowing the next day that the coffee costs €1.50 does not provide you any additional information about the value of the coffee. On the other hand, if you are traveling to a foreign country, you don't know what is the cost of the coffee. Over the days, over multiple days and multiple coffees, you will accumulate information about the value. So the amount of information that we acquire by ordering a coffee and by measuring the outcome of X, will have a certain entropy, and each time you will observe the outcome, this will be exactly the amount of information that is carried by the given variable. Okay, I'm going a bit fast, but I hope I was clear enough to give you these measures. So basically, the entropy can be understood in two different ways. One is the amount of uncertainty in a given random variable, and also the amount of information that a given random variable is carrying. The third measure, information theoretical measure, is what is called the joint or conditional entropy. So if you have a single variable, okay, this is the definition of the entropy. But if you have two variables, you can also have a definition for the joint entropy, meaning that you may want to know the cost of a coffee, whether you are ordering like a ristretto, an espresso, or like a long coffee. So this is X is the cost of what you will pay of the coffee, but then Y is, say, the size, okay? So this will produce different values of uncertainty, and also a relation between the two values. So there are some generalization, and there are very simple mathematical definitions of the joint entropy and also the conditional entropy.
Andrea,
Yeah,
maybe if I can briefly ask. So
sure.
I'm starting to get a bit concerned about my health. So given that there is a distribution like PXY, as you said, it's the price of a coffee at a certain location and maybe a certain coffee type. I'm afraid I need to drink quite a lot of coffee in order to estimate such distributions. How How would this work in practice?
Exactly. So in practice, the solution is not going to be to test yourself all those coffees because it will be very bad for your health. But we can do like a Gedanken experiment, like thinking more in abstract way. But you exactly got the point. So the basic measure, the basic quantity that you need to estimate is the joint probability distribution, as you may have seen here. So the probability distribution of X, which are the variables. So this is exactly the tricky part which we are confronted in everyday life. And I will go into the details of this later in the methods. But basically, there are two large categories of methods that can be used. In one category of methods in which you cannot have any kind of a priori about the shape of your probability distribution in a kind of non-parametric statistical way, you will need to estimate this probability distribution from the data. One of the simple methods is to go and test all the coffees in all the bars, in all the regions and so on. Then you create like a histogram, like a data set, and then you will be able to transform your histogram into a probability distribution. This is very time consuming and you need a lot of data to do this, which is not the case when you do a PhD, when you don't have enough and you're a researcher, when you don't have enough time and you have very few data points in your trials and experiments. So the solution most of the time you will see later is to make approximations about the probability distribution. And one of the simple ways to assume that the probability distribution or the marginals are Gaussian, for example. If you can do this, or if you can transform the data to be Gaussian, and there are some tricks to do this, then things actually become much easier because you can have approximations and you can estimate the probability and the entropy values from fewer time points. But just be patient. I will show you all this in a few slides.
Thanks, that makes sense.
Thank you for the question. Okay, so the next measure that Shannon introduced is what is called the mutual information. The mutual information, as you may have heard already in your past seminars and so on, is a quantity that defines statistical relations between two variables, X and Y. Okay, so if X is the cost of the coffee and Y is the country, for example, where you are, you may have like a relation between them. And the definition that is defined of information, of mutual information, is very simple. And it's basically is defined as this difference between two uncertainty measures. So we've seen that H of X, which is the entropy of X, which is the uncertainty in the cost of the coffee, okay, could be some kind of value, say 2.5 bits, let's say. Now let's say where that Y is a second variable, which is the town or the country where you are in. So the two variables are linked together. Because, for example, in the cost in Germany or Norway or in the south or in the south of France or in Italy is going to be different. So if the uncertainty in the cost of your coffee of X, given that you know where in which country you are, so given Y, if this amount of uncertainty is lower than the first term, then the difference between the two is going to be positive. That means that the two variables X and Y are somehow related. And the difference between the reduction, so is the reduction in uncertainty in the marginal entropy, is going to give you the amount of information that Y carries about X. On the other hand, let's suppose that Y is not the country in which you are, but is, say, the weather in Sydney, okay? The two variables actually don't have any statistical relation between them. So the second term, the uncertainty in X given the weather in Sydney, is going to be equal to the uncertainty in X. So the difference between the two is going to be zero, and this will give a zero mutual dependence between the two variables. So the mutual information quantifies the amount of correlation, the amount of mutual information between X and Y. There is a graphical version of this if you look on the website of the Wikipedia, which is very simple. So imagine that two variables are linear related. Okay, so now the correlation between them, x and y, is very strong, so it's 1. Then if you add some noise, this can be reduced to 0.8, then 0, then can become negative. The mutual information is very similar to linear correlation, so to the Pearson correlation, for example, but it's going to tell you only whether there is any type of statistical dependence between the two variables, being either positive or negative correlation. So here on the top right of each panel, you have the value of the mutual information, and you see that for linear correlation, the two are very similar. The same for linear positive correlation, then they're both 0 when there is no statistical relation between the two variables, but then the mutual information becomes positive again if there is any type of relation, can be either positive or negative correlation. The main difference between mutual information and linear correlation is that mutual information can tell you whether there is any type of statistical relation being linear or non-linear. Here you may have a statistical relation between two variables which is more complex, such as a U-shape, or it can be like a circle and so on. In this case, a linear correlation, of course, because it assumes that there is a linear correlation between the two variables, will tell you that the two variables are not statistically dependent. It would be 0 for this case and also for these other 4 cases. But on the other hand, mutual information will tell you that there is a positive value, meaning that the two variables are statistically dependent. Both will give a 0 value if the two variables would have like a linear and 0 correlation, and then, for example, repeated for 4 times. Okay, so this was like the intuitive version of linear correlation and mutual information. Finally, and this is going to be the last measure from the classical informational theory that is going to be useful for your project, is based on the conditional mutual information. So the conditional mutual information is defined here, and basically is nothing but, again, a subtraction between two conditional entropy values. So the conditional mutual information is tightly linked to a measure that was introduced at the beginning of 2004, I think, which is called transfer entropy. Well, originally it was a very similar measure which was called directed information, was introduced in the 90s. But then this measure was reinvented, as it sometimes happens in neuroscience and also in different fields. And then now is most of the time called the transfer entropy. But the underlying idea was very similar, very similar. Basically, once you have two time series from which you are recording the activity, say from the first brain region and the second brain region, one question that you may want to have is there any statistical relation that is present between the two time series? Is there some kind of directionality? So in information theory, people have been using what is called the Granger causality principle, which historically comes from the Wiener definition of predictabilities. So defined in the 50s and then formalized by Grangers in 69 in the economic field. That's why it's called the Granger and Wiener causality, which states that if there is a predictability from the past of a signal to the future of another signal, the receiver, which is lacking, which is absent in the past of itself, in this case, you would say that there is a directional relation between the green signal to the red signal. This is defined as the Granger causality, Wiener causality principle. And this has been formalized in information theoretical framework in terms of conditional mutual information between the past of the green signal and the present of the receiver conditioned on the past of itself. And this is exactly the definition that you see here. So the condition, the transfer entropy, so the amount of what could be interpreted as the information flow between the green to the red signal is defined as the time-lagged mutual information between the present, so at time t of the receiver, the past of the source at t minus d, condition, so which is not present in the past of x, which is t minus d. This measure mathematically is defined as the difference between the entropy of x only, so x given the past of itself, so it's the uncertainty in the next value of x given its past, minus the uncertainty in the x of t given its past, and, so the comma here means and, the past of y. Imagine now that y does not have any kind of statistical relation with the present of x. That means that if you remove this, if you add or if you remove this variable here, the entropy does not change. That means that if you remove this term here on the right side is going to be equal to the first term, meaning that the difference between the two is going to be 0. So in this case, if the two conditional entropies are identical, in this case, you interpret this as a 0 transfer entropy, so a 0 information transfer from y to x. On the other hand, if the fact of knowing y, the past of y, has some value, meaning that it can be used to be reduce the uncertainty in x of t, this term here will be lower than this, and the difference will be positive. In this case, so you will have a net information flow or an information, so transfer entropy between x, between the green to the red signal. Be careful also to use terms as transfer, information transfer, and so on. I prefer to use terms such as directional relations, directional statistical relation between the two. Information flow is something that is a bit more probably abstract, and there are different ways to calculate information flow, and there is no single information flow measure. Still, transfer entropy is one of the accepted measure of information direction, information transfer, information flow. The advantage of information of transfer entropy is that it's asymmetric, meaning that if you want to know if there is a flow of information between the green to the red, you will use this formula. But if you want to know whether the red influences the future of green, you just need to replace y with x. And in this case, you will have the information flow from x to y, meaning that these two measures are not identical. And this is the main difference with respect to mutual information, which gives you a single value between the two measures. Okay, so these are the five definitions in classical information theory. And then I would like to show you a few more recent measures that has been introduced thanks to some theoretical development in information theory, which came out in the last 15 years, more specifically in 2010, which is called partial information decomposition. So we don't have time to go through this literature because it's going to be a bit time consuming. But in a few words, partial information decomposition has been developed to try to formalize mathematically how we can decompose the multivariate mutual information between multiple variables such as x and y and a single target variable, say, for example, the stimulus type. So this the decomposition of multivariate mutual information has been very tricky in the literature, and the partial information decomposition introduced in 2010 by Williams and Beer has proposed a mathematical way to decompose the information theory into different terms. And intuitively, you can have a measure here of say the mutual information between a single variable c and two variables x and y. They could be, say, the brain activity of region x and the brain activity of region y. The partial information decomposition states that the total mutual information is composed by 4 terms. The first term is the information that it's common to both x and y about, say, a target variable c, which is called the redundant information. Then there is a second term, which is called the unique information, which is the green part carried by x only. There is a unique component, which is carried only by x, which is here in orange. And then there is a fourth term, which is called the synergistic information, which is the red area, which is the amount of information that is carried only if you know both x and y. Don't be scared. Let's look at an example here, which is going to clean up a bit the ideas. Imagine now a standard example is like in vision, for example. We have 2 eyes, okay? Imagine the x and y are the 2 eyes. It's an information carried by the two eyes about the given object. So imagine that you are looking at a complex scene and the information that it's carried only from the left hemifield, say from the left eye here in orange, is called the unique information that is carried by the left eye. Then there is one part of the visual scene which is only seen by the right eye. This is the amount of information that is carried only uniquely by the right eye. And then there is one part which is common, which is the information that is seen by both the right and left eye, which is defined as the redundant information by the two. So redundant is the common one, and then unique only left and only right eye. On the other hand, there is some extra information that is present from the scene that you can have access only if you have only both eyes open. If you close one eye, you won't have this. And this is the 3D, the information, which could be associated to the synergistic information, which is present only if both eyes are present, which is this extra information that is contained and is present in the system. If you want to read the details, you can have a look at this paper here, which is only by archive. Like a funny thing is that this paper has revolutionized one part of information theory, has never been peer-reviewed. So it has never been published in a real journal, in a journal, always been only in a bioarchive manner. I mean, luckily it was correct. So most of the math, I mean, it's a math paper. So the ideas were correct and it kind of revolutionized. So meaning that there is also something which is interesting from this perspective, publishing perspective. Okay, so let's go back to our stuff, which is trying to make sense about the functional connectivity between two brain regions and an external variable, which could be the stimulus type or the behavioral response, which is C. So over the years, we've been using these approaches, and I suggest you to have a look at this review from TINS, which came out recently from Andrea Luppi, which allows to calculate not only the amount of the interdependence between X and Y, say the mutual information, but also the amount, the kind of informational content. So is the coupling between X and Y informative about a third variable, which could be C, the cognitive variable? One example of these measures that we have been looking at is this measure, which is called feature-specific information transfer. And again, I'm sorry we don't have time to go through the methods in detail, but if you want, you can have a look at this paper that we published last year in NeurIPS. And basically, in 2 lines, this measure is a generalization of what I showed you as the transfer entropy, in terms of the ability of a measure to measure to quantify the amount of information that is transferred about a given stimulus. So imagine that you have measured the activity of two brain regions, X and Y. As I showed you before, you can use the the conditional emission information to calculate the transfer entropy from X to Y. This will give you an idea of the amount of directional influence from the past of X to the future Y, and you can interpret this as the amount of information flow between X and Y. On the other hand, it does not tell you what is the amount of information flow between X and Y about, say, a given cognitive task or a given stimulus feature. So the goal of this measure is exactly to try to quantify a sub-quantity which is bounded by the transfer entropy, so the transfer entropy here in gray, and a subcomponent of this information could be about a given experimental manipulation, say the stimulus type, being an apple or a pear. In the partial information decomposition framework, so we use this PID, partial information decomposition framework, to formalize this measure. And intuitively, you can understand this fit measure, so feature-specific information transfer, as the redundant information that is present in the past of X and in the present of Y, so which is common in the two signals, which is unique, so which is not present in the past of Y. The mathematics is a bit more complex, so the real definition is not exactly as this, but it's just to have a rough idea, you can visualize in this way. I'm mentioning this because part of the latest tool that we developed and implemented in FRIT, actually they contain this measure that we recently introduced. So more global, you can also have a measure, have a look at this paper that came out in Journal Neuroscience last year, in which we tried to apply these ideas to simulated data, trying to provide different measures or try to provide like a theoretical framework linking the so-called Mars level, going from the computational to some kind of primitive, some kind of metrics that allowed us to identify some kind of basic computations from neuronal activity, such as the transfer entropy or the storage of information or the mutual information between two brain regions, or the synergistic, so the information modification between different brain areas. I'm sorry, we don't have time to go through the details, but you can have a look at this paper, and then probably during the practical, the week, we can talk about this again. Another paper that you can have a look is a recent paper that came out this year on eLife, in which we applied these methods to study the brain networks and the neural interactions in the frontal cortex in two learning conditions, such as learning from rewards and punishments. And we managed to calculate and to dissociate redundant information, synergistic information in terms of coupling between two brain regions. So these are the two most recent papers that you can have a look to have an idea of what are the types of applications, the types of analysis that can be performed. There is also another latest paper only on the bioarchive that actually I didn't put on the slides, which is a paper that I put on the bioarchive last week, which is an MEG data analysis in which we study functional connectivity, both synergistic functional connectivity and feature-specific information transfer between brain regions during learning. So if you type, the first author is Etienne Combrison, I'm the last author. There is a bioarchive which is on synergistic interactions, and there again you will see type of application going from the analysis of local activity using FRIT, going down to the information flow. So to sum up, these are the latest developments based on information theory. So this paper here, you can have a look at this review and these two papers, this and the eLife paper. which are based on the latest developments from information theory applied to the analysis of neuronal time series. To go back and wrap up a little bit this most theoretical part, I would like to show you another paper which was very instrumental for developing these tools by Robin Ince, and I really suggest you to have a look at this paper, which was actually the starting point of our development for about FRIT, which is our toolbox. And this is a table in which Robin made a link between information theory and other classical statistical approaches. Because in fact, information theory can be used as a kind of common statistical language to do a different set of statistical analysis on your data. So you may want to calculate, for example, the mutual information between two continuous variables, okay, univariate continuous variables. In this case, you will have a measure which is going to be similar to like the Pearson correlation, Spearman correlation, or the rank correlation, and so on. If your data is discrete, okay, this will be the mutual information between two discrete variables would be, say, a chi-square test of independence or an exact test. If you want to do some, if you calculate the conditional mutual information, this or the direct information, in this case, you will have something which standard is range of causality or a partial correlation in statistical analysis. And then you have different more complex measures such as interaction information and so on that we also implemented in FRIT, which are related to, say, representational similarity analysis or mediation analysis when you have more than two variables. But the great contribution from this paper was to show that if you transform, or to remind us that if you transform the data to make it Gaussian, things become much, much easier. And this going back to the question from Mikael. So how do we calculate these measures from the data? So here on the left, you have the general equation of the mutual information, which is, as I showed you, is the difference between the entropy of a given variable minus the conditional entropy. If the two are identical, the difference is zero, so there is no relation between S and R, X and Y. How do we calculate this? One way, as I told you, is to estimate the probability, the jump probability or the conditional probabilities, and then to calculate the entropy values. On the other hand, if your original data, say, is not Gaussian, as in this case, but if you create like some kind of manipulation and transform it to be Gaussian here, okay, such as using what is called like a Gaussian copula. So copula meaning that it's linking to manipulation of the data. You can use some simplifications from maths. So by sticking into the equation of the entropy, the equation of the Gaussian distribution, the mutual information boils down to be like as the logarithm of the determinant of the covariance matrices. Sigma x is the variance of x, sigma y is the variance of y, and sigma xy is the covariance of the two. So what, at the end of the day, you need to calculate is simply the variance and the covariance of your data, which you can calculate from much less data points, say 100 or 200 data points. So in terms of generality, so here are some examples. You may want to calculate, say, the mutual information between your brain data and a discrete variable, which is, say, the experimental condition or the type of stimulus, okay? So discrete 1 or 0 or 1. Or you may want to correlate, say, your brain data between, so your brain data with the reaction time, so some kind of continuous variables. In this case, you will have the same kind of code to calculate, slightly modify the mutual information between continuous variables. Or you may want to be also in the case of conditional misinformation, where you want to know if there is a relation between the brain activity and, say, reaction times or speed or learning, for example, conditioned on the experimental condition, say easy or hard learning condition. This is feasible with the same kind of formalism within information theory framework. Then what the toolbox contains is a second set of methods that allows you to do also statistical inference on these measures. And very rapidly, there are different kind of categories of statistical inference that you may want to use. For example, you may want to consider all your neurons or all your subjects in a kind of single subject analysis in which you are calculating, for example, the presence of a given effect in the population. Or you may want to find like a common, like the fixed effect in your population. For example, you are recording 100 neurons from the same subject. You may want to calculate the fixed effect, or you may want to study the population as a random variable. So you may want to calculate, for example, imagine that you have 50 subjects, 50 participants in your MEG study, and you may want to know if there is any kind of you can do any kind of inference about the generality of the population. In that case, you may want to model the effect using like random effect analysis. So these three different statistical or types of statistical group level analysis need, however, in neurophysiology to be linked with standard permutation tests or problems related to the multiple comparison problem. This is a standard issue in neurophysiology because it's something that you always face once you analyze large data sets. You may want to analyze and make some statistics over multiple time points over time, over multiple electrodes, or even multiple frequencies. In that case, you will need to take into account the fact that you're repeating the same statistical analysis over multiple time points and over multiple electrodes, and in functional connectivity analysis over multiple pairs of channels. So this is going to be problematic because as the network size increases, say you have 100 or 1,000 neurons or 1,000 brain areas, the number of pairs of comparators is going to be increased a lot. In order to assess correctly the level of significance, then you have to correct for these multiple comparisons. And there are a number of sets of statistical tricks that needs to be implemented to correctly infer the statistical significance at the group level, which have been developed over the years, especially in different softwares such as Filtrip and so on, then developed and implemented in mini Python and so on. And these are linked to standard permutation-based statistics in which you don't want to assume any type of distribution of your data. But what you do to try to assess the significance, you generate permutables, or you destroy the relation between the brain activity and the behavioral data, for example, by permuting the trials. And in this case, you generate surrogates from which, or null distributions from which you can calculate and assess the significance of your original data set. So to give you an overview of the toolbox, so the first part in our toolbox is related to the inference of measures of information theory from the core functions information theory. And then the second block is exactly contains the tools that allows you to make statistical analysis using different types of approaches, from single subject to random effect, and then to combine it with permutation-based statistics and multiple comparison correction.